Okay, so pretty quick, just a couple more things to finish off this section of the book. And we want to talk about confidence intervals for the variance now. And we can get a small sample confidence interval for the variance of the population under the normal assumption. So we have to assume the population itself, not just an estimator, but the population is normal. I don't need to estimate mu squared or sigma squared, but I need to assume normality. And then theorem 7.3, which we've used a lot now, says that n minus 1 s squared over sigma squared chi squared n minus 1 degrees of freedom. And the confidence interval follows quickly from here. So one thing is this chi squared PDF is not symmetric, so we need to just pick 2 points. The common one is to pick the end points, so we know 1, let's say 1 minus alpha. If I split this, probability Q chi square alpha over 2 n minus 1. Okay, that gives me the alpha over 2 quantile for chi squared is n minus 1 degrees of freedom less than or equal to n minus 1 s squared over sigma squared less than or equal to q chi square 1 minus alpha over 2 n minus 1. And we can now just invert these. So yeah, let's call this, maybe give this the name like the book would probably use. Is like this would be x, little x, maybe 1 minus chi squared over 2, because it uses the right tail, the opposite of what x chi squared. Okay, so it uses the probability to the right of that quantile for this kind of notation in the book. So it would then be equal to taking the reciprocals and multiplying through by n minus 1 over s squared. We get this is the probability that n minus 1 s squared over x over 2 is less than. And there's your confidence interval. Okay, it's not symmetric, so you don't have a center and radii, but there you have it. So for example, if we have, say, we assume normal and say we have 10 samples, so say n equals 10, s squared equals 3.75. I don't remember if this is from another example or not. Say we want alpha equal 0.05, then this little x squared 1 minus alpha over 2 is here, and something like that. And this is equal to 2.7, and x squared alpha over 2, this is here. And this would be equal to 19 about. And then you have your confidence interval becomes, so let's see, I have 2.7 times, sorry, I have a 30, so we get the left endpoint becomes, so the confidence interval, so 95% CI is equal to, what do I have here? 9 times s squared So that's going to be about 30 something divided by 19. So the left end point, I just did this ahead of my time, but yeah, let's see. So I get n minus 1 s squared over x alpha over 2. This turns out to be 1.77. And if I do the other one, over x1 minus alpha over 2. This is going to be much bigger. This is about 12.5. And so this is a small sample confidence interval for the variance of whatever this data was. Okay, so yeah, if I wanted the a confidence interval for sigma, I could take the square roots of these numbers, right? That would be valid too. So if we wanted, because this inequality would hold under the square root, so this is 4 and 95% CI. Sigma is just take the square root of each of those numbers and we get 1.33. Again, the meaning is for intervals that are computed this way, 95% of them capture sigma. Okay, so 95% of such intervals as this one was, the way this was computed based on random data, capture sigma. So we're 95% confident that this one captures sigma. Okay, one more example for variance. So we can compare the variance of two populations using the same theorem. So suppose I have x1 to xm, normal, mu, say 1, sigma 1 squared, unknown, and y1, yn, normal, mu 2, sigma 2 squared, both unknown. And so then 7.3 what we have m minus 1, let's call it sx squared over 1 squared chi squared with m minus 1, n minus 1 sy squared over sigma 2 squared chi squared n minus 1. And from the definition of an f random variable, we can set f equal to the quotient of these divided by their degrees of freedom. So f is equal to, let's say, sx squared over sigma 1 squared over sy squared divided by sigma 2 squared. And this has an f distribution with m minus 1 numerator degree of freedom and n minus 1 denominator degree of freedom. This is a positive random variable, and it's defined this way to be the quotient of two independent chi-squared random variables divided by their degrees of freedom. Okay, so, or degree of freedom. Okay, anyways, here we have it. So if I want say I want a 1 minus alpha CI for, let's say, sigma 2 squared over sigma 1 squared. I see that this will come up into the numerator here. We could say, again, f is not symmetrically positioned on the axis. So I have 1 minus alpha equals probability QF. I'm using this f random variable as the pivot, alpha over 2, m minus 1, n minus 1, less than or equal to f. So sx squared over sigma 1 squared, sy squared over sigma 2 squared, less than or equal to qf, 1 minus alpha over 2, m minus 1, n minus 1. Okay. Right? Yes. And I can now just multiply by these. So we get our confidence interval is just probability. After multiplying, I get sy squared over sx squared. And yeah, let's call that f1 minus alpha over 2. I'm not taking any reciprocals here. I'm just going to bring this up into the numerator. So this is the right one for this. So less than or equal to sigma 2 squared over sigma 1 squared, less than or equal to, again, this is the same, sy squared over sx squared, f alpha over 2. And this is my confidence interval here, right? Right. This is smaller than this, right? This is on the left side, this is on the right side. This is the same on both. So this makes sense. And it will give me a confidence interval for the ratio of the variance of the second population to the first. Could be useful if it's near 1 with high probability. Like if I have a very narrow confidence interval around 1, then maybe I can assume that the variances are the same. The populations have roughly the same variance. If, it's not, if it's much bigger than 1 with a fairly narrow band, then maybe I know the variance population 2 is much bigger than population 1. If it's very near 0, maybe I know the population of 1 has a higher variance than the population of 2, or at least with high confidence. Okay, I don't think we need a numeric example for that. That's it for this part of the course. So we started with some initial concepts and stuff from probability, sampling distributions, and order statistics. And then we got into point estimators, some general notions of point estimators, as well as 4 examples of unbiased point estimators that have low variance if the sample's big. Then we got into confidence intervals, centered confidence intervals for large samples that exploit the central limit theorem, as well as just single sample confidence intervals for many different types of distributions, or at least we looked at 3 or 4 or 5 of them. Finally, some confidence intervals with small samples for both the population mean and the population variance. So that's what the course has been so far. And we will continue onward.